In this video, we're going to be taking a look at our Voltaic Cell activity, which is on page 7 in Unit 9. And so this is we're setting up a Voltaic cell in real life, and we're setting up a copper zinc Voltaic cell. And so you can see here on this list of materials that we're going to see in a moment. And we've got a diagram down here showing us how we are going to set this up. So I'm going to pause and flip over and show you what this setup looks like. Okay, so we're going to set up our Voltaic cell here. Notice we're going to set this up under standard conditions first. So I've got two beakers. One has 1 molar zinc sulfate in it. One has 1 molar copper sulfate in it. And then what I need for my Voltaic cells, I need some electrodes. So I'm going to stick this piece of solid zinc and put it over here in my container of zinc sulfate. I'm going to take this copper and put it over here in my copper sulfate. And then I am going to connect them by a wire here. And so notice how this is running through a voltmeter. It's going to measure our voltage. So let me turn this on here. And right now our voltage is 0 because it is not hooked up to anything. So we're going to connect this side to our copper electrode. And then I'm going to connect this side over here to our zinc electrode. And they will notice the voltage is still reading 0. And that's because right now we're missing a key part of the Voltaic cell, and that is the salt bridge. So the salt bridge is just something through which ions can move freely. So what I'm going to do, very simple salt bridge, I'm going to take a piece of filter paper. This is something we use for chromatography. And I'm going to dip it in here in a solution of potassium nitrate. So these are non-reactive ions that aren't going to interfere with my cell. And so I'm going to make this nice and wet here. So I've got this wet piece of filter paper, and then I'm going to put it in here so that one side of the filter paper touches this solution, the other side touches the other solution. And now what happens is the ions can flow freely through this piece of filter paper. And now if you take a look at our voltage, now we're getting a voltage reading. And it's saying our voltage is about 0.9. Okay, which is a little lower than I expected it to be, but there you go. That's reasonable here. So that is our voltage here for our standard cell. So I'm going to pause and look back at our Onenote page. Take a look at our Onenote page here. We just saw that our actual voltage here that we just measured in the lab was 0.9 volts. And we saw that when we remove the salt bridge, when there was no salt bridge, then it was 0 volts. So our cell has 0 voltage if there is no salt bridge. And that's because that when you think about the purpose of your salt bridge, it is to maintain the charge neutrality of the solution on either side. So with no salt bridge, then you're going to have a charge buildup. Sorry, my handwriting is messy here. So you're going to have a charge buildup, and then your voltage is going to drop to 0 there. So you need that salt bridge for that cell to work. And let's think about what we predict the voltage to be. So if you look over here, we've got these two reactions that are given. Notice how they are both examples of gaining electrons. So these are both reduction reactions. So these are what we call standard reduction potentials. And if we think about our relationship with delta G equals negative NFE, we know that the more positive the E value gives us a more negative delta G, which means, and more negative means more favorable. So I can take a look at these reduction potentials, and the one with the more positive reduction potential is the more favorable reaction. So this one is it's the more favorable reduction. So that's the reduction that's going to happen. And if we think about where does reduction happen, well, remember anox and then red cat. So reduction occurs at the cathode. So at the cathode, this reduction reaction is going to occur. And so the reduction potential, so the voltage of that reduction is 0.34. And then the one that's not as good at being reduced, that one's going to be oxidized. So this one, zinc, it's the less favorable reduction. So if you flip it around, it's going to make the more favorable oxidation. So I'm going to flip it around into an oxidation. And when you flip the reaction around, the sign changes. So now it's positive 0.76 volts. So we got two favorable reactions here. And then if you add them up, you get the overall cell potential is positive 1.10 volts. So what we got is a little bit lower than that. It's actually decently lower. And keep in mind, this is under standard conditions where all solutions are 1 molar and the temperature is 25 degrees, which our temperature is definitely probably not that right now. Okay, so now let's take a look at what happens under non-standard conditions. So now what we're gonna do is we're gonna set up another cell where instead of the solutions both being 1 molar, your copper solution is going to be very dilute. It's going to be 0.01 molar. And then your zinc ion solution is still going to be 1 molar. So we're going to see what impact that has on the voltage. Okay, so let's take a look at what happens when we change our standard cell into a non-standard cell. So this is a much diluted solution of copper. Okay, and we are going to and notice how the standard cell is reading 0.91. So what we're going to do is we're going to swap this around. I'm going to put my copper electrode in here, and I'm going to transfer my salt bridge over here, and we're going to see what happens. And it looks like the voltage dropped. Not a whole lot, but the voltage did drop a little bit, which is what we're expecting to see happen. So when you lower the concentration of copper, copper ions are a reactant. So if you decrease the amount of reactant, you're going to see your voltage drop. If we decrease the concentration of the product, we would see our voltage increase. And if we'd increased the reactant, then the voltage would go up. So you can think about these different relationships here that would happen. If we were to dilute both of these solutions by the same amount, like if we were to make both of these solutions 0.1 molar or make both of them like 2 molar, then the voltage would stay the same. So as long as these two solutions are of equal concentration, the voltage will match what we'd expect for a standard cell. But if you change the concentrations of one of the solutions, then it will change the cell potential. And that's what we call a non-standard cell here. You can look at these non-standard conditions. There's some hints here to kind of get you to think about this in terms of Le Chatelier's principle. So we can think about equilibrium concepts from Unit 7 and trying to explain why a voltage might increase or decrease in a certain conditions. So if you have fewer reactants, the forward reaction is going to be less favorable. So if it's less favorable, that means your delta G is less negative. So if you got less favorable delta G, you're going to have a smaller voltage. And that's what we saw in this example. So that's one way to kind of think it through in terms of Le Chatelier's principle. But the other thing I want you to do is to read through page 7b, talks about a Q versus K argument. And so take some time to read through this. It's a little bit meaty. There's also, so you might want to underline some things, highlight, take notes to yourself. I also, in AP Classroom, I assigned this video here, 9.9, daily video number 1. It's just like a 9-minute video if you want to kind of hear through their preferred method of explaining it, which is kind of what is covered on this page. So it's a Q versus K argument. So read through this section from the textbook. You can watch this video. And then also down here at the bottom, I tried to summarize it in as simple as terms as possible right here in terms of like how you would explain what's going on with these non-standard cells.